Assalamu alaikum. I am Sumbul Zehra from Sir Syed Government Girls College. With the support and guidance of our principal Professor Khalda Parveen, today I am here again to deliver lecture on electric field due to a ring of charge. Now, coming to our topic, which is electric field due to a ring of charge on a point on its axis. Before we have studied electric field due to different charge distributions. But today we will do one more thing. If there is a ring of charge, so we have considered a metal ring and we give it a charge, and charges are distributed all over the ring. So where do we want to find out an electric field if this is a ring and we make it charge and charges are distributed automatically all over it? And do you know what type of charge distribution is this? Ring has an area, but the charge is distributed on the length of the ring. So we have linear charge density, and this linear charge density is denoted by lambda, which is lambda equals to Q upon L. So we have to find out an electric field on the axial line. This point is on the axis of the ring, where we have to find out an electric field on a point on its axis. Because charges are not in a straight line and their addition will give us a complicated result, and it is not simple like a point charge. So I want to find out a calculation of electric field at the axis of the charge ring, and its center is of course the part of the axis. So I will add into this electric field due to a ring of charge on a point on its axis. So this is a ring of charge. It is a three-dimensional diagram as you see, and I just convert this into a two-dimensional point, and we have to find out the electric field at this point P. We know we have only one formula for electric field, that is 1 upon 4 pi epsilon naught q over r square, which is with respect to a source charge. There is no source charge at the center, so who will make the electric field? So all the charges on the ring make electric field, and the total net electric field will be sum of that, and we will work on this strategy. How we will work on that strategy? How much electric field is at point P? So according to Pythagoras theorem, the hypotenuse value of this right angle triangle is under root r square plus x square. So here electric charge is distributed and we have to give certain quantities in terms of which we have to find out the value of electric field. After all, we have given two things to us. This ring has a radius r and the charge we have given to it is lambda. So we have to find out electric field intensity value E at a point P, which is at a distance x from the center of the ring. We know the formula for point charge here. It is length. So first we have to convert this length into a very small length, just like for point charge. So far we have learned whenever we want to convert a bigger thing into a smaller point, we take the help of a calculus. So we take a very small length here, dl. dl is very small, so it can treat it as a point. So here we are permitted to use formula for point charge if length is dl. Now what will be the charge on this length dl? On a small length dl, the charges are lambda dl equals to dq. This will make electric field at a point as dE1 equals to 1 upon 4 pi epsilon naught lambda dl upon r square plus x square. So what is the direction of this electric field? Direction of this electric field is along the line joining the two. Now, if I take another dl which is dimensionally opposite, which is dE2. Now again hypotenuse is under root r square plus x square. So value of electric field dE2 is 1 upon 4 pi epsilon naught lambda dl upon r square plus x square. Now we see magnitudes are same for both but directions are opposite. Another thing we can take out, because of this geometry, we take an angle theta. As you see in diagram that the electric field dE1 divide or resolve into its two components dE cos theta and dE sin theta. One is along the axis and the another is perpendicular to axis. Same for dE2. When we take 2 points diametrically opposite like dE sin theta, for both electric field will be cancelled out and we get resultant electric field which is dE cos of theta in the direction of axis. This is when we take 2 points diametrically opposite. When we take 2 points diametrically opposite, we have another diameter also. So for every electric field, dE sin theta of one point will be cancelled by dE sin theta of another point. Then what will be the resultant electric field? Resultant electric field is summation dE cos of theta. So what is the value of dE cos theta? Value is summation 1 upon 4 pi epsilon naught lambda dl upon r square plus x square into x upon under root r square plus x square की power 1 by 2. So if we combine and calculate this, we are left with the value of electric field which is summation 1 upon 4 pi epsilon naught lambda dl x upon r square plus x square की power 3 by 2. If dl is closer to 0 or approaches to 0 and adding of all dl, so in close integral for whole circle of the ring is 1 upon 4 pi epsilon naught lambda dl x upon r square plus x square की power 3 by 2. Now value of dl is equals to 2 pi r, which is the circumference of the circle. So close integral become 1 upon 4 pi epsilon naught lambda 2 pi r x upon r square plus x square की power 3 by 2. If total charge is q, then q equals to 2 pi r lambda. Then equation of electric field becomes equals to 1 upon 4 pi epsilon naught qx upon r square plus x square की power 3 by 2. This is our expression for electric field due to a ring of charge on a point on its axis. Now we can compare this with the general formula for point charge, which is E equals to 1 upon 4 pi epsilon naught q over r square. So the only difference is in the value of the r, which is equals to r x upon r square plus x square की power 3 by 2. Now we will consider special cases of this ring of charge. Number one case is when distance is much greater than radius of the ring, then we can neglect the value of r from the equation and equation become E equals to 1 upon 4 pi epsilon naught q over x square. So we have seen that when distance is very large, this whole ring will act as a point charge. Second condition is when distance is much less than radius, which is at the center where x equals to 0. When x equals to 0, then electric field is 0 at the center. So these two are the special cases of the electric field of the ring of charge. Right. So that's all for today. Thank you so much.